Verification, validation, and uncertainty quantification is a field with specialized terminology that can sometimes seem a bit overwhelming. The subtle nuances of these terms are essential for conveying precise information. However, if everyone isn't on the same page, it can quickly lead to confusion. Hi, I'm Josh, and welcome to the VVUQ channel, and today we're going to examine a standard published by the American Society of Mechanical Engineers, or ASME, which tries to put everyone on that same page. ASME VVUQ-01 provides simple definitions for all the key terms you'll come across. Plus, it offers valuable insights into each of these terms, making it easier to navigate the world of VVUQ. On top of all this, the good folks at ASME intentionally made the standard free to encourage you to download it, use it, and share it with your friends. For more information on the ASME committee or to download the standard, check the description below, and sit back, relax, and enjoy as we explore ASME VVUQ-01. In this final video, we're going to talk about uncertainty quantification and finally credibility assessment. Uncertainty quantification includes error, uncertainty, and uncertainty quantification. And credibility assessment, the very last section of the standard, includes the concepts of applicability, predictive capability, and finally credibility. And to me, it's really interesting that credibility is the very last term defined because credibility is legitimately the whole reason anybody cares about this. And maybe it should be the first term defined, but it's kind of like what we're building towards. So those are the definitions we'll be tackling in this fourth and final in the ASME VVUQ-01 series. First, error. Error is defined as the difference between a measured or calculated value and the true value or its proxy. This is a very common definition for error. You can find it in almost any textbook. It's recognizes, I think this definition specifically recognizes that, hey, we'd like the true value, but we may not have it, so we have to use its proxy. In this document, we've defined that proxy as the referent. The other interesting thing is a lot of times things are talked about in terms of error, but they might talk about it, if you want a more better marketing term, you don't talk about the error, i.e. how bad something is. You talk about its accuracy, i.e. how good something is. So you might say the accuracy of a model, you can usually read that as the opposite of the error of the model. So error, we've talked about a bunch of these already. So we have code verification error, which is the difference between the mathematical model and the computational model. We've had solution verification error, what we said is the difference between the computational model on that infinite computer and the computational model on that computer with limited resources. We've talked about the validation error, which is really just the difference, including uncertainties, between whatever values in the real world and whatever value our computational model says. So error, the difference between a measured or calculated value and the true value or its proxy. And it's just error is equal to the true value minus whatever your estimate of that value is. So with defining error, we can now define uncertainty. And uncertainty is defined as the recognition of imperfect knowledge about a system or quantity. We generally separate uncertainty into two main types, aleatory and epistemic. These are really fun terms because I have not heard any terms get people more upset than these two terms. But I think the standard does a really good job of staying away from getting people upset. It just says, hey, look, usually epistemic, we mean incomplete understanding or incomplete information. Epistemic comes from the word for knowledge. So it's like we don't understand something about it. Aleatory, inherent variability. Aleatory is usually associated with dice. I think it even comes from the Latin for dice player. Uncertainty, you can think of, hey, we've got all these great measures. We can measure things, we can calculate things, we've got computational models, but they're all kind of fuzzy. They all have that uncertainty, and that can be due to lack of knowledge or just inherent variability. So uncertainty, the recognition of imperfect knowledge about a system or quantity. The world is fuzzy for multiple reasons. So finally, uncertainty quantification in this small section, and that is defined as the process of generating and applying mathematical models to provide a measure of uncertainty in the empirical data or simulation results. So one of the things this standard really wanted to do was not only define uncertainty quantification's use in modeling, but also define its use in experimentation, because we need to quantify the uncertainties in experiments before we compare them to the simulations. Uncertainty quantification is kind of broken up into two different areas. One, characterizing the uncertainty, and the second one, propagating those uncertainties. So characterizing, basically you're trying to figure out, okay, I've got uncertainty in this thing. How do I model that uncertainty? it's in a quantity, it's in a system, whatever. How am I going to model it? That's characterizing it, and then finally propagating it. Okay, now I've got this uncertainty, I've got it modeled. How do I determine the impact of that uncertainty on those quantities of interest that I care about? And again, you can do this for a computational model, you can do this for an experiment. So the world is fuzzy. We need to somehow relate that to the fuzziness in our computational model. So the process of generating and applying mathematical models to provide a measure of uncertainty in the empirical data or simulation results, that's uncertainty quantification. It's just saying, hey, I've got this fuzzy world. I need to represent this in my fuzziness of my model. Finally, we can go to the last section, the credibility assessment section, and we can begin with this word applicability. And this is I'm going to say it's a newer concept. In nuclear, we have a very similar term called scaling. Applicability is such a better word. The relevance of the evidence from the verification, validation, and uncertainty quantification activities to support the use of a computational model for a context of use. Okay, that says a lot. What does that really mean? Again, this is an area it's often overlooked. It's really tricky. One way to think of it, hey, is your verification applicable? You performed all these verification activities. When we talked about verification, if we talked about code verification, let's say we verified that at a certain set of inputs, our mathematical model matched our computational model. But when we want to make predictions with our model, chances are we're going to want to change the inputs, and we probably won't have results from our mathematical model to be able to verify it at that new input. So can we use the assumption that our code is verified in one region as we extrapolate it to another? Same thing with validation. Is your validation applicable? Does this, hey, I've compared to this experiment. Great, you've compared to this experiment. Your computer code perfectly matches the experiment. Does that experiment behave like the real world system you want to make predictions of? This is a huge deal. There are multiple examples of computer simulations that have done a great job of predicting experiments and a horrible job of predicting reality because the experiment did not match the real world system that they intended to. I think visually applicability is easier to understand. So applicability is just, hey, we've got two kinds of domains in our space. We've got some X1, X2, X3 space that we're working in. We've got all of our VVUQ data in one little corner of the space, and now we've got the pink square will be this application domain. That's where we want to apply the model. And here we have decent overlap. We have the VVUQ evidence is really close to where we want to apply the model. Great, awesome. So we would say the applicability there, hey, it looks good. But what if, well, that application domain is far from where we have that VVUQ evidence? Now we might question things. I mean, our model could have done a phenomenal job where we have that evidence. It might have extremely low uncertainty in terms of validation. Code verification is great. But if it's far from where we actually want to apply the model, we're going to have some questions, and those questions will be captured in terms of applicability. Applicability, the relevance of the evidence from the verification, validation, and uncertainty quantification activities to support the use of a computational model for a context of use. I just like to think of it as, hey, you've kind of gotten this three-dimensional space, and you can kind of see, like, I've got one box where I'm close to my validation data and the other box where I'm kind of far from my validation data. Do I really want to use the model in both of those cases? So this leads us into predictive capability. And predictive capability is really a realization that where we're going to use the model, we probably won't have data. So we need to come up with an accuracy for our model. So predictive capability is the anticipated accuracy of the computational model for conditions where no empirical data are available. In other words, we quantify the model's error in one domain, but we want to use it to make predictions in another. We just talked about this in applicability. What do we expect the model's error to be in that new domain? So we got to figure out something. Well, this is predictive capability. And this seems to rely as much on rigorous quantification as it does on engineering judgment. So for example, here is a similar representation as what we said before. Now we have certain points in this domain where we have, hey, we know the values predictions, we know the uncertainties of our computational model at these points because of our VVUQ activities. But the problem is we don't want to make predictions again at those points. We actually want a prediction out here. And we don't really have any data out there, so what should be our uncertainty? Should it be this? Should it be bigger? Should it be really big? Figuring out what that uncertainty is basically you're determining the model's predictive capability. And if I go even further out, my uncertainty might increase. If I go closer to the data, I might decrease my uncertainty. The anticipated accuracy, which again, remember I said is just basically, it's a fancy way of saying it's a nicer way of saying error. You could have also said the anticipated error, but the anticipated accuracy of the computational model for conditions where no empirical data are available. With that term defined, we can finally, and there's the cool picture of it. We can talk about credibility. Now, credibility is the reason we're out here in the first place, the reason the standard exists. It's the main concept. If you summed up VVUQ in a single word, you would call it credibility. Credibility is the trust established through the collection of evidence in the predictive capability of a computational model for a context of use. That is a lot of terms to say something that I think can be easily understood as basically credibility is a binary judgment. You have a computational model, you want to use it to answer your question of interest. You're going to make a prediction with that computational model. Can I trust the prediction from my computational model for whatever thing I'm using it for? Can I trust it? Yes. Can I trust it? No. Is it credible? Is it not credible? That's what credibility is about. It's not a level of trust. It's just, can I trust it? Yes, no. You're going to find many such judgments are made by individuals throughout the assessment process that are linked to credibility. If you're developing a model, you're not going to turn it over to the next person in the process until you determine it's credible. If you're assessing the model, you're probably not going to finish your step until, oh yeah, I think it's credible. I don't think anybody's ever going to say, oh yeah, you can't trust this model, but I'm going to give it over to the next guy. My job here is done. And it's important to realize that credibility can be changed because it's based on the model's given purpose. So credibility is, can I trust the model for its context of use? It's important to remember that because let's say go back to the beginning and I have my model of a bridge and I need to create a computational model and I need to make sure that the bridge can withstand 600 pounds. So I do a finite element analysis. And I say, oh yeah, I've done this great analysis. The bridge can withstand 600 pounds. Great, but to really understand if I think the model's credible, I need to understand, well, what are the consequences of being wrong? Like if the bridge collapses, is this bridge over a stream and I just fall into the stream and maybe my legs get wet? Or is this bridge over a 500-foot chasm and if I fall into the chasm, I'm not going to survive? Understanding the consequences of getting the model wrong are needed to understand if you can say the model is credible. In other words, we can trust the model. What does credibility look like? You have someone that sits in judgment and they're basically weighing two things. They're weighing the consequences from that question of interest and they're really weighing that VVUQ data. And they're trying to determine, okay, is the model credible or is it not? And you have two choices for the verdict. It is either credible or not credible. Either you're going to trust the model or you're saying, nope, I can't trust the model. Go figure out something else. Credibility, the trust established through the collection of evidence and the predictive capability of a computational model for a context of use. And it's just those scales. All right, let's recap. We began with defining error and said that it's just the true value or the value that's the closest you can get to the true value minus your value. Then we talked about uncertainty, how it's basically stuff we don't know, and uncertainty quantification, basically how do we handle those things we don't know. Then we went to the last section of the document, the credibility assessment. First, we talked about applicability, how this is really understanding that you've performed VVUQ analysis at one portion of the domain, but you're likely going to want to use your model at another portion of the domain to make predictions. And so you're asking, is all of this VVUQ evidence applicable to where I actually want to use my model? And then we ask the next logical question, what should I consider as the accuracy of my model when I make the prediction? Finally, we talked about credibility. Given the question of interest, given the consequences of getting it wrong, given all the VVUQ evidence we provided, we have to decide if we can trust the results of our computational model. Remember, you can download the standard using the link in the description. It's freely available, so feel free to take it, use it, share it with your friends. Additionally, I made the PowerPoint presentation available, so feel free to take that, use that, and share that as well. Finally, in the comments below, please let me know what you found wrong and what you thought was useful. Thanks for watching.